Good morning, students. Let us study today Transconductance Amplifier. In the previous class, we have studied the voltage amplifier. In this class, we'll study the Transconductance Amplifier. This Transconductance Amplifier is also called as series feedback network. This is a block diagram of Transconductance Amplifier. It consists of the basic Transconductance Amplifier and a feedback network. The input function generator is given at the input side. The role of feedback network is output is connected back to the input, and this will generate the voltage as VF. V0 is given back to the input and that voltage will be VF. This is a circuit diagram of the transconductance amplifier. This complete block diagram is shown in terms of the circuit diagram. Why we have used a op-amp or the differential amplifier? Because we need for the transconductance amplifier two inputs. One is Vs, function generator voltage, one more is Vf, which is the feedback voltage. As we know that our A1 or the op-amp has two input terminals, one is inverting and one more is non-inverting. Pin number 2 is inverting, pin number 3 is non-inverting, pin number 6 is output voltage. We need to give Vs to one of the input terminal and we need to give Vf to the one more input terminal. So we have taken this op-amp. Now it also consists of a common source stage Q2. Vs is given to the inverting terminal. The output voltage V0, which is potentially divided between RL and RF, which generates Vf, is given to the non-inverting terminal of the op-amp, and then this is given to the common source voltage, common source stage Q2. Now, the output voltage V0 is fed back to the same thing what I have told now. The V0 is fed back to the non-inverting terminal of the op-amp through RL and RF. The voltage will be Vf. Now we need to check here one point, that Vf and Vs should have the same polarity. Now similar to the voltage amplifier, what we have studied here, the input impedance is large because we have used a series connection. Vi, whatever we get, which is Vs minus Vf, which is small, II is small, so resistance is large. Same thing I have written here. I'll just write here. As in case of feedback voltage amplifier, the series connection at the input results in the increased input resistance. The reason is Vi is Vs minus Vf. So Vi is small, II is small, resistance is large. So same fashion we get the input resistance as large. Second point what I have written here, the figure B consists of differential amplifier and common source stage Q2. Next what I have written, output is fed back. And next I have written the point, both should have the same polarity. Now we'll see the working of the circuit. The positive change in the Vs, when I apply the positive voltage little more, then the voltage at this point is negative. The positive change in the Vs will result in the negative change at the gate of the Q2, which in turn causes the increase in I2, which increase in I2 causes the positive change in Vf, which has the same polarity assumed for the Vs. So from this we'll say that the feedback is negative. I'll repeat once again, the positive change in the Vs, the working of this circuit, positive change in the Vs, inverting terminal we are giving, it gives the negative voltage at the gate of Q2, which increases I0, which causes the positive change in the Vf, which has the same polarity as Vs. From this we'll conclude that this has the negative feedback. Now we'll take some mathematical formulas of this circuit. Some mathematical formulas like open loop gain A. Open loop gain A is equals to, we'll be using I0 upon Vi. Why we have taken I0 upon Vi? Because this will give me the output voltage here as I0 and the input here is Vs. So open loop gain becomes I0 upon Vi. The next formula is feedback factor beta is equals to Vf upon I naught. Feedback factor is given by Vf upon I naught. Next is closed loop gain. Closed loop gain AF is given by A1 into Gm square by 1 plus A1 into Gm square into Rf. We all know that A1 Gm square Rf will be very much larger than 1. So AF can be written as A1 Gm square divided by A1 Gm square into Rf. These terms will go, then I can write AF closed loop gain as 1 upon Rf. I'll just revise once again the transconductance amplifier. This much you should write in the exam. I think so you followed this concept. I'll just repeat once again what all what we have done just now. The transconductance amplifier is also called as the series feedback network. This consists of, the first point is the transconductance amplifier is also called as series feedback network. First point. Second point, it consists of basic transconductance amplifier and a feedback network. The role of this feedback network is to fed the output back to the input, which will generate the Vf. Now, third point is, as in case of the feedback voltage amplifier, in this circuit, the input resistance is large. In this circuit, the input resistance is large. Input resistance is large. How we get? Because Vi is Vs minus Vf. This is small. Ii is small. So resistance is large. Figure B is the circuit of the transconductance amplifier. It consists of op-amp followed by common source stage Q2. Now here Vs is given to the inverting terminal and the Vf means the V0 whatever get potentially divided and we will get Vf. It is given to the non-inverting terminal. Now here they should have the same polarity. Working of the circuit is the positive change in Vs will give it is given to the inverting terminal. Here negative voltage, it is given to the gate, which causes increase in I2, which causes positive change in Vf. So finally we will say that this is the negative, this gives the negative feedback. Next we'll take the transresistance amplifier. Before that, we'll take some mathematical formulas. Open loop gain is given by I0 upon Vi. Open loop gain of this circuit is I0 upon this Vi. The feedback factor is given by the formula Vf upon I0. Next is closed loop gain is given by A1 Gm square by 1 plus A1 Gm square into Rf. This value is larger than 1, so this is neglected. So we'll be having this much. Then the closed loop gain will get the answer as 1 upon Rf. Next we'll take the transresistance amplifier. Next we'll take the transresistance amplifier. This is called as shunt amplifier. Why it is called as a shunt amplifier? Because at the input side we take shunt connection, parallel connection. At the output side we take the parallel connection. The transconductance amplifier is called as series because at the input side we have series connection, at the output side we have a series connection. Whereas in transresistance amplifier, we'll have parallel connection at the input, parallel connection at the output. Now we'll draw the block diagram of transresistance amplifier. Consists of transconductance and feedback network. Now just see, we will be having shunt connection. How we'll give that shunt connection? This is shunt connection at the input, parallel connection at the input, and similarly parallel connection at the output. So it is called a shunt amplifier, and the output voltage is measured across RL. Here input signal is current, IS. Input here is current and output signal is voltage. Here the input signal is current and the output here is voltage. The shunt connection at the input causes the input resistance to be reduced. In the transconductance amplifier, series connection at the input causes the resistance at the input to be increased, whereas here the shunt connection at the input causes the shunt connection at the input. It causes the resistance, input resistance to be reduced. Input resistance to be reduced. And similarly, shunt connection at the output also reduces the output resistance. So how we'll write it? The shunt connection at the output stabilizes the output voltage, and thus causes the output resistance to be reduced. Now, this block diagram can be drawn as the circuit diagram, where again we need two inputs. So we'll go for the op-amp. Op-amp has two input terminals, minus and plus, inverting, non-inverting. Non-inverting terminal is grounded. The input IS is given to the inverting terminal, and we want that feedback voltage. So RF is used. So V0 is fed back to the inverting terminal. So we get here IF, feedback voltage, and then II. This is the circuit diagram of the transresistance amplifier. I'll mark it as figure A and I'll mark this as figure B. Now, in figure B, the op-amp is used. This is our op-amp. Feedback resistance RF is also used. RF provides the feedback current IF, which is subtracted from IS at the input node. I'll repeat once again, or I'll write some points otherwise. Here in figure B, op-amp is used and feedback resistance RF is connected, and feedback network feedback resistance RF is connected. This RF provides what it will give you, the feedback current IF. Yes, no, this will give you feedback current IF, which is subtracted from IS. Which is subtracted from IS at this point. Now we should see that the feedback is negative. So how we'll see it? IS is increased. Then II will also increase, causing the output voltage here as negative. Input terminal to rise. In response, output voltage will decrease, causing increase in IF. Thus, IF and IS have the same polarity and feedback is negative. I'll just repeat this point once again. I'll just write here. To see the feedback is negative. Now I have to check if the feedback is negative for this circuit. So what we'll do? IS is increased. IS is increased at this point. Then what will happen? II will increase, causing voltage of negative input terminal to rise. And this is increased, voltage at this point will increase. So what will happen now next point? Output voltage will reduce, causing the increase in IF. Let's write here. In response, output voltage will decrease. Why the output voltage will decrease? Is will increase, II will increase. This is given to the inverting terminal. So output voltage is negative. So output voltage will decrease, which is causing increase in IF. Thus, IF and IS, they have what? Same polarity. And now feedback is negative. This much you should write for the trans-resistance amplifier. I'll repeat once again the trans-resistance amplifier. The trans-resistance amplifier is also called as shunt amplifier because input side we have parallel connection, output side we have parallel connection. It consists of basic transconductance amplifier and a feedback network. Feedback network provides the feedback path. Then we have, actually the input signal here is current, output here is voltage, so IS is used. RS is in parallel and RL we have here. Since we have used a shunt connection at the input, so input resistance is small. Since we have used here the shunt connection at the input, so input resistance is small. Similarly, we have used the shunt connection at the output, so output resistance is also small. Same the thing is drawn in terms of the circuit diagram like this way, where IS is given to inverting terminal and this terminal is grounded, non-inverting terminal is grounded, and the RF provides the feedback path. It provides the feedback path. Now we'll see some points here. Now I have to show the feedback is negative. So how we'll show this? We'll see that the feedback is negative. How we'll show that? The IS is, when IS is increased, the II will increase. It is given to the inverting terminal. So output voltage will reduce. Then when the output voltage will decrease, which causes the increase in IF. Since the IS and IF, they have the same polarity, the feedback becomes negative. So this much is the trans-resistance amplifier and transconductance amplifier. If you have any doubts, you can ask me personally to my WhatsApp number.